Now, we've treated the topic of finding LU decomposition before, but it doesn't hurt to go over it again, and we can use some of the concepts we've been developing to go through this at a little bit more thorough, maybe more deeply understood level. All right? So, for any given matrix, there are many different LU decompositions, but there's a unique LU decomposition in which the L matrix has ones on the diagonal. In fact, typically, this is the LU decomposition that's talked about in other textbooks, that you require that the L matrix has ones on the diagonal. In this case, L is called a lower unit triangular matrix. So there's only one LU decomposition where the L part has only ones on the diagonal. All right. So we'll do this the same way we did before, which was associating row reduction operations with lower triangular matrices, and then kind of working backwards. All right? So we'll see how this works for a single stage in this simple example. Here we have an elementary matrix. This matrix corresponds to adding lambda times the first row plus the second row and replacing the second row with the result. Okay, so like this lambda is in the second row, first column, and what that means is you replace the second row with lambda times the first row plus the second row. All right, so we see that here. This second row here is lambda times the first row, you can check that, plus the second row. And you can also check that this result is what happens when you multiply this matrix times this matrix. The other fact that's very critical here is that the opposite operation to adding lambda times the first row to the second row is subtracting lambda times the first row from the second row. So this matrix here is the inverse of this one, because this corresponds to the subtracting the same constant, and you can check that that's true. Right. So what that says is that EM is equal to this, and if I want to recover M from EM, I need to multiply EM by E inverse. All right, so this is the backwards operation that takes us back to the original matrix. So we see here how the inverse of the row reduction matrices takes us back to the original matrix. All right, so let's do this on a particular example with row reduction. Here's our M. Now, what you'd like to do is create a 0 here and a 0 here. That's typically what you do when you do row reduction. You zero out the entries in the first column under the first entry. All right? So that corresponds to two row operations. In this case, in order to zero out these two entries, I'm going to have to take minus 1/3 times the first row plus the second row. And I'll also have to take minus 1/3 times, minus 2/3 times the first row plus the third row. Okay, that gives me two elementary row operations. The first operation is R2 minus 1/3 R1, it's this matrix. Second one, R3 minus 2/3 R1, it's this matrix. I can combine these two into a single matrix, which is basically the product of this one times this one. You can actually check that these two matrices commute. It doesn't matter if I subtract the first row from the second row first or from the third row first, I get the same result. So when I combine these two, I get this operation here. All right, so I know that M times this matrix, so let's call this one A. I know that AM has, there's a 6 here, and there's stuff here. I know that AM has zeros here, and there's more stuff here. All right. So I want to get M as a LU. I'm going to take M is equal to, if I multiply both sides by A inverse, I'll get an A inverse over here. And then this is going to be 6 and something, and 0 and something, and 0 and something. All right? This is not completely upper triangular, but we're getting there. Now, what about A inverse? A inverse is this same matrix here, but replacing the negatives with the positives. Remember, in order to undo the operation, subtract 1/3 row 2 from 1/3 row 1 from row 2, I can add 1/3 row 1 to row 2. Okay, so A inverse is going to be this same matrix here, but with the minuses replaced with pluses. Okay, so that gives us 1, 1/3, 1/2, 0, 0, 1, 0, 0, 1 times, and this is going to be what you'd call U1. All right, and again, this U1 is not completely upper triangular, but we're getting there. So let me go back to the text, and you see that that's what he has here. We have M. Here's my U1, which has zeros in the first column under the 6, and here's my L1. All right. Now, if I repeat the process, if I do a row operation to get rid of this 3, which is going to be minus 1/2 of row 2 plus row 3. All right. The elementary matrix for that is going to be a diagonal with a minus 1/2 here. But then to take the inverse, the minus 1/2 will become a plus 1/2. So you can see that the result is going to be this. Now let's take stock of what we're doing here. Let's go back to our scribbles here. Oh, sorry, this should be, sorry, I missed something missing here. It should be M equals this times U1. Now, what are we doing here? We have our A times M is this. So applying to A times M, we're taking this L2, which is 1, 0, 0, 0, 1, 0, 0, minus 1/2, 1. And this is equal to U2. So that means that M is equal to, well, we have the U2 here, and I have the inverse of this one, 1, 0, 0, 0, 1, 0, 0, minus 1/2, 1, and sorry, that's kind of messy. 0, minus 1/2, 1. I'm taking the inverse of that because I can apply the inverse to both sides, and I'm taking A inverse here. Now this A inverse was the matrix I had before, which had the 1/3, 2/3. So that was 1, 0, 0. And then this one was 1/3, 1, 0. And then this was 2/3, 0, 1. And then I'm multiplying by the inverse of this on the right. So that's 1, 0, 0, 0, 1, 0, 0, 1/2, 1 times U2. All right, and now this U2 is actually upper triangular. All right, and that's what we have here. This L2 is lower triangular, and in fact, it's unit lower triangular. It has 1s on the diagonal. And then here I have an upper triangular. So our LU decomposition is actually finished. Okay, here's a video that does another example. All right, sometimes these LUs are kind of ugly, as they said. Now, what you can do is switch constants from one side to the other. It turns out that for two matrices LU, we can multiply one entire column of L by a constant lambda and divide the corresponding row of U by the same constant without changing the product of the two matrices. Now, you might wonder, why is that? Well, for instance, in the matrix product, if I take this matrix times this matrix, the entries in the second column always multiply entries in the second row over here. You can check that. So if I multiply all these entries by a number and divide these entries by the same number, that's not going to change any entry in the matrix product. Another way of seeing that is shown right here. For instance, suppose I want to multiply the first column by 3, second column by 6, and the last column by 1. All right. Then I can break up the identity matrix in this way. This product is just the identity matrix, right? The 3 here and the 1/3 cancel here, 6 and 1/6. 1 and 1 is the same here. So I can group these two together and group these two together. This one here is going to multiply, this 3 is going to do what? Well, every time I multiply this 1 by the 3, it's going to multiply the first, column, because it's always the first column that multiplies that 3, right? And then this 1/3 is going to multiply the first row, because it's always the first row that multiplies this one. All right. So if I accomplish this, I group these two, I get this one. If I group these two, I get this one. And you can see that in this matrix, the first column has been multiplied by 3. To get from here to here, multiply by 3. To get from here to here, multiply by 6. And to get from this one to this one, well, you multiply the first row by 1/3 and the second row by 1/6. All right. So you can shift the burden around, get rid of these fractions at the cost of making these bigger. I mean, at the cost of making these fractions. All right. So it's just kind of a trick. Now, if you have matrices that are not square, you still can find the LU decomposition, because you can still talk about above the diagonal and below the diagonal. But you have rectangular, so it's not going to be quite so nice and neat. All right. So here's an example. If I have this matrix and it looks like this, then we want to zero this one out, and to zero this one out, we would subtract 2 times the first row from the second. The inverse of that is adding 2 times the first row plus the second. And if you accomplish that on this result, you'll get this result here. Now this one is lower triangular, because diagonal above the diagonal is 0. Here the diagonal below the diagonal is 0. All right, so this is our final LU decomposition. Now, one more topic here. We saw before that you can take a matrix, divide it into blocks, and basically perform matrix multiplication as if these blocks were numbers, as long as you break your matrices up into blocks of the same size. Now, it turns out we can do LU decomposition in the same way. We can divide the matrix up into blocks and then perform matrix LU decomposition as if each one of these matrices were just a number. Remember, when we do Gaussian elimination, we have to divide by numbers, but here we can do the same thing by taking inverses. As long as all these matrices are invertible, we can do that. But we would need to make these blocks square in order to get inverses. All right, so you would definitely need to have square blocks on the diagonals in order to make this work. All right. So when you do this LU decomposition, for example, with 2 by 2 decomposition, you'd get something like this. And this is the exact formula. Now notice something. Here I actually have a lower diagonal matrix here, because this block is I, this block is I. If you think about all the entries above the diagonal, they'll all be 0. Same thing here. I have a lower diagonal, an upper triangular matrix here. Did I say it right? This one's lower triangular, this one's upper triangular. And this matrix here is not really a diagonal matrix, it's called a block diagonal matrix. Because this X may have entries off the diagonal, but the block itself is on diagonal. So for instance, X could be a 2 by 2 matrix. It may have a single entry below the diagonal, but as I said, the block is situated on the diagonal. All right, so that's possible to do, and you can check that just by multiplying those matrices together. Okay, that's it.